we talked about the Wittig reaction for last class, and it was a reaction of a part of the reaction of aldehydes and ketones, where CO double bond changes to CC double bond. So when you have alkene, there are two sides of the molecule. One side of the molecule, it comes from alkyl halide originally that has been changed, like the alkyl halide that has been changed to the Aldehyde reagent. So here what is showing is the phosphorate Aldehyde reagent, but the Aldehyde reagent needs to be prepared in the reaction. So you don't purchase the phosphorus Aldehyde. Is coming from the triphenylphosphine plus the alkyl halides, and then you add a base, organic base, in order to remove a hydrogen. And when you remove the hydrogen, you will get the Aldehyde reagent. So aldehyde plus the Aldehyde or ketone, aldehyde or ketone plus the Aldehyde would give you alkene. One side of the molecule that shows in green color here, that is coming from aldehyde or ketone. So if it's aldehyde, it's going to have one hydrogen and one R group. And if it's a ketone, both of them would be R groups. And the blue side is coming from, the blue part is coming from the alkyl halide, where your alkyl halide, originally the alkyl halide that you choose based on the number of carbon that you need to add to the other side. You're using a primary alkyl halide here, and that's what it gives you alkene with one hydrogen and one R group on the side that is coming from the alkyl halide or from the Aldehyde reagent. You need to know, as I said last class, that how to prepare the Aldehyde reagent. Yes, recapping from last class. And then, but you don't have to be worried about the actual mechanism for the Wittig reaction for your next exam. So, the example of the Wittig reactions, like with the retro synthesis. Okay. You have trouble viewing the PowerPoint? Can you see the PowerPoint, or you're not, you cannot see the PowerPoint? Because I'm on slide number 32 now. Can you see the slide number 32 or no?
Professor, at least for me,
Okay. Okay,
just the title page, yeah.
Just the title page. So let me restart. Better? Okay. Okay. Perfect. The example for the Wittig reaction, to prepare alkene using a Wittig reaction, we are going to cut the molecule through carbon-carbon double bond. One side is coming from aldehyde or ketone, and the other side coming from the Aldehyde. So you have this side of the molecule coming from the Aldehyde. And when you look at the Aldehyde, I mean, if you don't want to, if the question is not asking for mechanism of the reaction, if you go back to this previous slide to how to make the Aldehyde, you see the carbon that carries the carbon that carries the halide, okay? Carbon attached to the halide is the carbon that is going to be attached to phosphorus in this Aldehyde reagent. So when you have your Aldehyde reagent, the same carbon that used to be halogenated, or the carbon that carried the bromide, in this case, it's going to be the one that is attached to the phosphorus. And then the rest of the chain is whatever you need to add. So with that in mind, if you go to the next example, see what we need to add here to the aldehyde or ketone. If we have the cut through this carbon-carbon, it's is like a allylic carbon, or carbon attached to carbon-carbon double bond. This carbon is going to be the one that it is attached to the phosphorus, and then the phosphorus and triphenyl phosphine. So this is the phenyl group, 3-phenyl group attached to the phosphorus, and the other side is attached to the carbon. So if we need to add these 3 carbon with this specific sequence, the carbon that is attached to the phosphorus is indicated as the carbon that is forming the new carbon-carbon double bond. And then the rest of the structure is going to stay the same. So we have this carbon and then carbon-carbon double bond attached to it. So this group, it's identical to the group that you want to add to the aldehyde or ketone as one part of the molecule in order to make the alkene. So when you are making the alkene, if you cut through this bond here, you would get one side coming from alkyl halide that has produced the Aldehyde reagent, and the other side from aldehyde or ketone. In this case, is going to be the aldehyde. There's no ketone if you cut through this molecule. Or the left side can come from the Aldehyde, and the right side from the aldehyde. So you could have this aldehyde, and then the Aldehyde that is coming from the left side. Now, you see the carbon that is used to form the new carbon-carbon double bond is attached to phosphorus, and then the rest of the chain is attached to that carbon, is bonded to that carbon. So the carbon skeleton of this side of the molecule does not change. You only add phosphorus with to that carbon, followed by the triphenyl phosphine, in order to make your Aldehyde reagent. To the other side, when you cut the carbon-carbon double bond, you're just adding a CO double bond. So you get your aldehyde plus the Aldehyde, or you get the aldehyde plus the Aldehyde. So you have 2 possible reactions. If you have any questions, make sure to write it use the chat to ask your questions. I will check to make sure I will answer your question before I move on to next type of reactions. So we are talking about the reactions of the aldehydes and ketones. We talked about some of the reactions like that about the aldehydes and ketones. We were talking about the last reaction that we talked was the Wittig reaction. So we talked about all the preparation of the aldehydes and ketones, and we are going to continue with the reactions of aldehydes and ketones. So one of the reactions was the Wittig reaction. Now, hydration of aldehydes and ketones. What does hydration mean? Hydration means adding water. And I keep saying adding water means add H and add OH. So that's basically the overall reaction when you are doing hydration or adding water. Obviously, when you add H will add to the oxygen because carbon-oxygen bond is polar. Oxygen carries slightly negative and carbon carries slightly positive charge. So is a partial positive, partial negative charge. So hydrogen is going to be added to the OH, and OH will add to carbon. So when you're doing hydrolysis, this is going to happen. You would get geminal diol. A geminal diol, that means that both OHs are on the same carbon. This is not a stable compound. Usually goes through dehydration. It would lose water. It would lose the H from one of the OH and OH together as a water, and then it changes to aldehyde or ketone. So whenever you have geminal diol, it can form, but is not very stable. So if you look at the arrow sign, the equilibrium that forms here, the arrow, the double arrow, it shows that reactant is preferred, and that means the reactant is going to be more stable than product. For the hydration, the mechanism of the reaction, it could be acid or base. It can happen in acidic or basic solution. If you have the acidic solution, because you are bringing proton first, then electrons from the oxygen is going to be protonated, but the arrow sign is always from electron rich to electron poor. So the oxygen is going to gain H plus. Okay, that H plus is going to be shared between oxygen and carbon, and then carbon is going to be positively charged, basically, because the H plus, the plus charge is going to be shared between carbon and oxygen, and carbon is going to be more stable with the plus charge compared to oxygen. Oxygen cannot take the plus charge. So it comes in and it will be transferred to the carbon. Now we have basically a positive charge on the molecule. You bring your nucleophile, water as the nucleophile. Because your nucleophile, we have seen this before, just to emphasize, because the nucleophile is neutral nucleophile and you have a positive charge in the molecule already, it's not going to form the product right away. So you have a intermediate with a positive charge on the oxygen, which is not very stable. And because oxygen is positive charge, we have to take care of that oxygen and the positive charge from the oxygen. And in order to remove it, you are removing H plus. So another molecule of the nucleophile or the solvent, it can remove the hydrogen with the plus charge, and you end up with net addition of water as adding H to oxygen and OH to carbon. That forms geminal diol. Questions? Adding cyanohydrin. Cyanohydrin formation is that what you're adding in this case is you have the CO double bond, and to CO double bond you add basically HCN. Okay. If you look at the molecule of HCN, it's positive, and then the CN is going to be negative. So hydrogen is going to be added to oxygen, and CN will add to the carbon. So you end up with CN attached to carbon and the hydrogen attached to the oxygen. So you end up with cyanohydrin cyanohydrin. Cyanohydrin, a functional group, is a carbon that carries both CN triple bond and the OH group. So basically, the other name for this reaction would be addition of HCN. It's like hydration was addition of water. In this reaction is addition of HCN. When you add HCN, H will add to oxygen and CN will add to the to carbon. And this happens obviously because the CO double bond is polar. So when you're bringing both nucleophile and electrophile, the electrophile would add to oxygen and nucleophile would add to carbon. Next reaction is reaction of aldehydes or ketone with amines. With a primary amine or with ammonia, the product is going to be amine. Okay. This is a amine, and amine is CN double bond. Okay. If you have either ammonia or if you have either ammonia or if you have primary amine, the product is going to be amine or amine. I just emphasized on the ine, so it's not amine anymore. It's the IMINE. That means you have a CN double bond. The pattern, this is not the mechanism. I just want to emphasize again, it is not the mechanism of the reaction, but is the pattern that is happening. Based on the pattern of this reaction, what happens if you have CO double bond? So you have CO double bond plus ammonia. So you have NH and then NH2. The pattern of this reaction, it's very simple. Two hydrogens, okay, from ammonia with oxygen is going to produce water, and then carbon with nitrogen is going to form double bond. So this is the pattern, it's not the mechanism, but that's how it works. So if you have, if instead of the H, if we have a Z group, you see that H, it remains here. If we had a Z group, that Z group would stay here in general. So if we have CO double bond plus Z NH2, that would give you C double bond N Z plus H2O. Okay. Now, if we have primary amine, what's going to happen in primary amine? You have R NH2. So R, it counts as the Z group. So when R counts as the Z group, the two hydrogen from the NH2 with the oxygen is going to form H2O. And the rest of the molecule is going to condense. Condensation, meaning combination of two organic molecules, and it gives you one organic molecule. And the new carbon-nitrogen double bond is going to form CN, and then we have the R group. In this case, that was the generally Z group that would stay, and the R groups from the ketone or aldehyde is going to remain. If you remember from last class, I said if you have a CN double bond and you hydrolyze it, if you add water, it will go back to CO double bond. So you hydrolyze imine is going to go back to ketone or aldehyde. So C and double bond, if you add water, it goes to basically the reaction, shows that the reaction is a reversible reaction. So if you have this general reaction, if you have, instead of the Z here, if you had OH, how would the product be different? You would have N, instead of Z, you would have OH. If instead of the Z, you had NH2, then on the product side, you would have N attached to NH2. So if you take this as the Z group, it would stay whatever is attached to this side of the nitrogen, other than the 2 hydrogen, is going to stay the same, and then only 2 hydrogen from the NH2 with the oxygen. This is the case that you either have ammonia, or you must have NH2 present, 2 hydrogen attached to the nitrogen. Okay, so if you have like an oxime, or if you have like for the hydroxylamine, you get oxime. Let me bring the examples. I do have a table that it shows all that, all those different type of functional group that could form. Okay. So NH2, the Z group here was the hydrogen, then the 2 hydrogen from the ammonia or from NH2 with the oxygen can give you the water molecule as a product, byproduct, and then the C and double bond forms, and the Z group, if it was ammonia, you had hydrogen. If it's a primary amine, the Z group is R. So again, is imine, is classified as imine. There's no new name for it. So if it's either ammonia or primary amine, you would get imine. If it's hydroxylamine, that means NH2 attached to OH, that's the hydroxylamine, you would get oxime as the product. What is oxime? It's just this functional group. It's a combination of, is a CN double bond that is carrying OH group. This functional group counts as oxime. Okay, in case if it's a question. If you have instead of the Z group, we have NH2, like hydrazine. Hydrazine is NH2, NH2. So you only need the 2 hydrogen from one of these nitrogen, and then the other NH2 counts as the Z group, and it gives you hydrazone. And basically, it's a precipitate. It's insoluble in water. So it's going to form actually a precipitate. And you have phenylhydrazine. How is hydrazine different from phenylhydrazine or phenylhydrazine? That's difference is that instead of one of the hydrogens, you have a phenyl group. So that's the N attached to hydrogen, and the other group attached to it is benzene ring. So there's really no need to draw all these bulky groups. With the general format or the general trend, as I said, we are not talking about mechanism of the reaction. The 2 hydrogen with the oxygen would give water as the product, and then the carbon would form double bond with this nitrogen. So you get the CN double bond and then NHPH. NHPH, this is like a phenyl added to the hydrazine and is phenylhydrazine. The product is going to be phenylhydrazone. Phenylhydrazone. If you have carbazide or semi-carbazide, again, the Z group is going to be different. Okay, you have a different Z group, and the final product is called semi-carbazone. So the 2 hydrogens, so we are looking for the same pattern, okay? two hydrogen from one of the nitrogens, or the first nitrogen that has the two hydrogen, is going to react with the oxygen from the carbonyl group, and then a C N double bond is going to form. The rest of the molecule is going to stay. So this table actually shows the different functional group that can be prepared or can be formed based on using ammonia, primary amine, or derivative of the primary amine or other. Okay. So we talked about addition of water. We talked about addition of HCN, the formation of cyanohydrin, addition of water that gives you diol, addition of ammonia, which gives amine, addition of primary amine that also gives you amine, and other forms of the primary amine, which is the NH2, followed by the Z group, whatever the Z group is going to stay for hydroxylamide, for hydrazine, for phenylhydrazine, and for semi-carbazide. They all basically fall into reactions of aldehyde or ketone with amines or ammonia. Next type of reaction is addition of alcohols. Okay, you want to add alcohol to aldehyde or ketone. To add alcohol to aldehyde or ketone, alcohol is not a strong nucleophile. So what would be the solution? You must bring a catalyst. So you have to bring a catalyst. In this case, acid would be the catalyst. So it's an acid catalyzed reaction. If you add one molecule of alcohol, okay, so right here we have if you have one molecule of, we add one molecule of alcohol. I was trying to bring a new slide, but we can probably use this same one. If we add one molecule of methanol to this ketone or cyclohexanone that we have, when you add alcohol, you just like adding water. So we have CH3OH, you add alcohol, basically meaning adding H plus and adding CH3O minus. Okay, so when you add alcohol, basically you're adding H and you're adding CH3O. H will add to oxygen and CH3O would add to carbon. So as a product, you're going to have OH and OCH3, both of them attached to the same carbon. This new functional group is called hemiacetal. Well, hemiacetal is like halfway to be acetal. Then what is acetal? Acetal is when you have carbon attached to OR, and this specifically is going to be OCH3 and another OCH3. If we call this acetal, OCH3 attached to the same carbon. When you have OH and OCH3 attached to it, it's like halfway to make to acetal. It's called hemiacetal. It's not acetal yet, okay? But hemiacetal would actually form first before acetal forms. So what are the steps? The steps, the first reaction here, the first step of the reaction or formation of the hemiacetal, it's addition reaction. So it's addition reaction to CO double bond. In addition reaction to CO double bond, I'm going to actually open a new slide or blank slide to use a new example. But what happens when you have the alcohol? Because it's not a strong nucleophile, you have to bring catalyst. So your catalyst is going to come in first. So catalyst is going to protonate the oxygen because it's H+. Just like before, when H+ comes in, it's going to bring the plus charge, and that plus charge is not going to stay on the oxygen. It is going to be shared between oxygen and carbon. So basically, your carbon is going to carry plus charge. And when carbon carries a plus charge, then the acts as a nucleus, then alcohol at that point can come in and form bond with the carbon with the plus charge, because alcohol is not a strong nucleophile. Okay, let me see if I can get. Okay, finally. So if we have, if we start with the same example or a different example, like the cyclohexanone plus the CH3, OH plus alcohol. Okay. In the first step, H+ must come in. Why do we need H+? Because this is a weak nucleophile. Because there's no, so we do need the catalyst. So when you have the catalyst would come in first, because that's the purpose of using the catalyst. Okay? When hydrogen comes in, it's going to bring the plus charge. So the plus charge is there. That plus charge is not stable on the oxygen, so pair of electron is going to go up. The plus charge, it will go down. So this is going to change to OH, but carbon is going to gain that plus charge. Now, we basically have a carbocation. In this step, the CH3OH is going to come in because oxygen has pair of one shared electron. And from the oxygen side is going to come and form bond with this carbonyl group. So we are going to have the cyclohexane. We have an OH group attached. And then the new bond that is forming is between oxygen and carbocation. So oxygen, CH3 on one side, H on the other side. What happens to plus charge? Our nucleophile is neutral in this case. And since it's neutral, is not going to cancel that plus charge. So we have that plus charge here. What is the next logical step? Is this a final product? Is it a final product? Could this be final product? What we need to do next? Can you hear me? Okay. This is not the final product. Okay. If it's not final product, what needs to be done? We have to take care of this plus charge, right? We have to remove that plus charge. And in order to remove the plus charge, another molecule of alcohol can come in and abstract this hydrogen. So if you bring alcohol, CH3OH, that is going to remove this oxygen, and you end up with OH on one side and OCH3 on the other side. This is known as the hemiacetal. Okay, so we have a hemiacetal. If you start from hemiacetal, it could be a product. If you start from hemiacetal and you want to add another CH3OH, and you need to use a catalyst because nucleophile is a weak nucleophile. In this case, take the first step of the reaction, these steps of the reaction, as addition reaction. Addition reaction. The first step is addition reaction. Second step of this reaction is a substitution reaction. What is a substitution reaction? The CH3O is going to, in the substitution reaction, CH3O is going to substitute the OH. But OH is not a good leaving group. Alcohol is not a strong nucleophile, so we have to use a catalyst. When we use the catalyst, in this case, OH is going to change to OH2 with the plus charge, and OCH3 is going to stay. Okay. Plus charge on the oxygen is not safe, is not good, is not stable. What's going to happen in this case, you cannot remove H plus, because if you remove H plus, it goes back to what we had before, and that's not beneficial. So instead of that, you have to remove water. So H2O would leave. Okay, so on the next step, H2O leaves. When H2O leaves, then you have OCH3 and plus charge here. Second molecule of the alcohol is going to come in. So you have OCH3 on one side, OCH3, but there is a hydrogen still there with the plus charge still in here. Because when alcohol comes in, is neutral and is not going to cancel the plus charge. So we have to make sure that the plus charge is removed with the hydrogen. So another molecule of CH3OH is going to remove this hydrogen with the plus charge, and you end up with cyclohexane with 2 OCH3 attached to it. OCH3. So first step, which forms hemiacetal, is addition reaction. Second step of the reaction is substitution reaction. There are 4 steps involved. And if you want to write down, because there are some applications to this formation of acetal or cyclic acetal as a protecting group. So we are using it. So if you have the, for the steps, for step 1 is protonation. Step 2 is addition, okay? Step 3 is if you don't mention about removing of the H plus, because that's kind of understood that you have to remove the plus charge. So it's like 4 major steps. Step 1, hydrogenation. Step 2 is addition of the alcohol. Step 3 is protonation of the OH. And then step 4 is going to be substitution reaction. So you end up with acetal as the final product. So when you have the hemiacetal, with the hemiacetal, you protonate the OH, it changes to H2O, H2O leaves, you have carbocation, and then the next molecule of the alcohol is going to come in and form the acetal, but you have to remove the H plus. So what you want to pay attention to this, all of these steps are reversible reactions. And if they are reversible reaction, that means if you have acetal, and to this acetal, if you have this acetal, you add H2O in presence of acid, is going to change to ketone, because it's a reversible reaction. You started with the ketone, and then you end up with acetal. But in this case, if you have the acetal and you hydrolyze the acetal, you would end up with ketone plus 2 molecules of alcohol. So basically, ketone plus 2 molecules of alcohol is going to give you acetal, and acetal plus water in acidic or hydrolysis of the acetal would give you ketone plus 2 molecules of alcohol. So this reaction is a reversible reaction. So you're dealing with a very reversible reaction, and there's really no preference here because the size of the arrow on each of them, they are equal. There is no preference which one is going to be more stable, which one is going to be less stable. And what is the benefit of that reversible reaction? So if you make like cyclic acetal, how could you make a cyclic acetal? In order to make cyclic acetal, instead of using 2 methanol, you would use 1 ethylene glycol. Both OHs are on the same carbon chain. So each one of these acts like as 1 alcohol. So in the first step, one of them would come in and form bond with the carbon, and would take the hydrogen. You have OH. Then second one would come in and replace the OH. So you end up with cyclic acetal. When you have cyclic acetal and you hydrolyze it, it can go back to aldehyde or ketone, and then the ethylene glycol would be removed. Acetals as protecting group. So if you have 2 groups, let's say if you have aldehyde group and a ketone group, which one is more reactive? Aldehyde is more reactive than ketone. So when you bring the ethylene glycol, it's going to react with aldehyde and not ketone. And if you were going to, let's say, reduce this, if you were going to change that molecule to this, let me make sure I have the right number of carbon. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So okay, if you were going to do this and you add like sodium borohydride, is this possible? Can you only change the ketone to secondary alcohol and do not reduce the aldehyde? You have 2 functional groups. If you want selectively, just reduce one and not the other one. So if you only want to reduce the ketone to OH, but keep the aldehyde as aldehyde, you cannot just add sodium borohydride. Instead of adding sodium borohydride first, you have to go through formation of this cyclic acetal. To this molecule now, after you make the cyclic acetal, if you add sodium borohydride, then you would reduce only the ketone to OH. And now to this, acetal that you have, if you hydrolyze this H2O with acidic, okay? If you have the H2O in the acidic solution, when you hydrolyze this, the hydrolysis of acetal would give you CO double bond. So you end up with CO double bond here, H and OH. So you cannot directly do this. You cannot directly reduce the ketone and keep the aldehyde. This is not going to happen. Instead, first you're going to change the aldehyde to cyclic acetal. Basically, you're going to use the cyclic acetal as a protecting group. It's going to protect the aldehyde functional group, because this is like a temporary. We saw that this is a reversible reaction, so it can go back with hydrolysis. You reduce the alcohol, do what you want to do with the ketone to change it to alcohol using sodium borohydride. Then you hydrolyze it and get the aldehyde back. So the idea of protecting group is like using a helmet. You just use that for going from step 1 to step 2, or from the initial location you have to final destination. And when you get to final destination, you remove that helmet. So it's just used as protecting group. So it's another example of, so basically it's continuation of that same reaction. With the sodium borohydride, you would reduce it, and then these numbers are separated. The reagents are separated by numbers. What does it mean if it's separated by number? That means that first you're adding sodium borohydride to reduce the CO double bond to OH, to secondary alcohol. Then you're adding acidic water to hydrolyze the CO, the acetal or cyclic acetal to CO double bond. Questions? Okay. Next reaction is oxidation of aldehyde. Aldehydes can be oxidized, but ketones cannot. You don't oxidize the ketones, but you can oxidize aldehydes, because the carbonyl group carries a hydrogen, so there's still room to add another oxygen to it. In order to oxidize, you would use oxidizing agent stronger than sodium borohydride, because sodium borohydride is not going to oxidize. Sodium borohydride is the reducing agent. I was trying to use that later on the next slide. It just came. So correction, oxidizing agent that you are using here, it cannot be PCC. PCC is the mild oxidizing agent, and it would oxidize primary alcohol to aldehyde. It can oxidize secondary alcohol to ketone, but it does not oxidize aldehyde or ketone further. So you have to use a stronger oxidizing agent from the aldehyde to carboxylic acid. So you can use hot permanganate, you can use sodium dichromate in sulfuric acid, or hot permanganate to go from aldehyde to carboxylic acid. The silver oxide also can be used like to oxidize the aldehyde to carboxylic acid. Next type of reaction. So there are a lot of reactions. You notice I told you beginning of the chapter, a lot of reactions. And some of the reactions I covered the mechanisms, others I didn't. The ones that I covered the mechanism, you'll be responsible, but the ones I did not, I just said know the pattern or the overall reaction. You are not responsible for the mechanism, but I did cover some mechanisms. Now, reductions, we have two reducing, we already know about two reducing agents, sodium borohydride and lithium aluminum hydride. Sodium borohydride is weak. Lithium aluminum hydride is a strong reducing agent. Sodium borohydride can reduce aldehydes and ketone. Lithium aluminum hydride can reduce aldehyde, can reduce ketone, can reduce carboxylic acid and acid derivative. So basically, in the reduction reaction, there are two hydrogens being added. One hydrogen is added to the oxygen and one hydrogen is added to the carbon. So if you have a ketone, it would change to secondary alcohol. If you have aldehyde, it would change to primary alcohol. Lithium aluminum hydride, same thing. It's going to reduce the aldehyde or ketone to alcohol. If you use hydrogen with the catalyst or catalytic hydrogenation, you just have to be worried about this carbon-carbon double bond. If you want to save the carbon-carbon double bond, so basically, if you want to get this product, okay, you cannot use H2 with the nickel or platinum or palladium. If you want to save the carbon-carbon double bond, you must use sodium borohydride to save the carbon-carbon double bond. But if you want to saturate the carbon-carbon double bond as well, you have to use the hydrogenation or catalytic hydrogenation. Reduction of ketone or aldehyde, like two-step reduction. For the two-step reduction, that means you want to remove the oxygen or deoxygenation of the aldehyde or ketone. We have seen this reaction before using Clemmensen or Wolff-Kishner reduction. CO double bond changes to CH2. So you have to use like two-step reduction. First, you go to alcohol and then tosylate the alcohol, then bring the lithium aluminum hydride if you were going to do in two steps, or use the reagent that you learned in chapter 17 about Clemmensen reduction. And the reagent for Clemmensen reduction was zinc, mercury, HCl. And then you have to hydrolyze it, add water. So zinc, mercury with HCl, it would change CO double bond to CH2. So you end up with deoxygenation or removing oxygen from ketone or aldehyde. Same thing for aldehyde. Clemmensen reduction works for both ketone and aldehyde. The only concern you might have is, or there should be concern, that this reagent is strongly acidic. Now, if your compound that you want to do reduction or remove the oxygen from, it's sensitive in acidic solution, then you cannot use this reagent. You have to use something that, like Wolff-Kishner. Wolff-Kishner is a basic reagent, and Clemmensen reduction is a acidic reduction, acidic reagent. So if your compound is safe in acidic environment, then you can use Clemmensen reduction, zinc, mercury, HCl. For Wolff-Kishner reduction, you do need to know the reagent mixture. What is the reagent mixture? However, you don't need to know the mechanism. Just know the reagent mixture. The reagent mixture that you are using here is going to be diethylene glycol, okay? Diethylene glycol and KOH, 175 degrees Celsius, at least recognize it, and then hydrazine, okay? So you have hydrazine and KOH, so, and heat. So in this reaction for the Wolff-Kishner, what you need to know is what the reagent combination is: hydrazine, KOH, and heat, and is the reactant ketone or aldehyde, the product CO double bond. Whatever the rest of the molecule is going to stay. The only change is that you would remove the oxygen. Okay, what is this diethylene glycol? What's the purpose of using this? You see that the temperature that you're applying is 175. So the solvent must have very high boiling point, otherwise the solvent would evaporate to, you know, dryness. This reactions should take in the, all of the reactions would take in a you know, liquid environment. So you must have it all dissolved in a solvent, proper solvent. Like when you're doing Grignard reaction, you're using ether because you want to stabilize the Grignard reaction. But at the same time, we know that that reaction does not require heat over like 56 degree or over, you know, 100 degree. So you can use diethyl ether. It's okay. But if you are using Wolff-Kishner and requires 175, the solvent cannot be diethyl ether. You must use a solvent that is going to be have very high boiling point to keep these all in the solution. So a lot to memorize in terms of reagents and what is the reactant, what is the product. I'm going to stop this because I want to separate the chapter 18 from 20.